We're told that light always travels in straight lines, but not always, because as we'll see, curved space-time can cause light to bend. Albert Einstein presented his full general theory of relativity in 1915, and it was finally published in the prestigious journal Annalen der Physik in 1916. One of the predictions from general relativity was that light should be bent in the presence of gravity due to the curvature of space-time. The calculations of general relativity predicted the amount of bending which could be expected, and Einstein gave a number for this angular deflection which should be observed if light was passing close to the surface of the sun. Einstein had published a paper in 1911 which gave a different value, but he had corrected his calculations during the completion of general relativity, and he finally predicted that light should be deflected by 1.75 arc seconds. But what is an arc second? Let's look at that because it will help to explain what Einstein's predictions meant in practice. An arc second is a fraction of a degree, so it is a measure of the angular position of one object, like a star, with respect to something else, like another star. So if we have two stars, we can work out their angular separation, and the units of that measurement are given in degrees or subsets of degrees. The full circle, a complete rotation, is taken to be 360 degrees. Then, much like how we divide up hours, minutes and seconds in a clock, we divide the angular separation of points in the sky into degrees, arc minutes and arc seconds. And in this way, 1 arc second is 1 over 3,600 of a degree, just like 1 second is 1 over 3,600th of an hour of time. To give an idea of scale, the full moon is about 1,800 arc seconds as seen from Earth. The exact size of the moon as seen from Earth varies because the orbit of the moon is not perfectly circular. But if we take its average size as being about 1,800 arc seconds, then we can see that the prediction Einstein made for the deflection of light by the sun was about 1,000th of the diameter of the moon. That is a very small deflection. Not only was the predicted deflection really small, and hence very tricky to measure, the other problem was how to measure this effect at all, since it required measuring light passing very close to the sun. The only light that passes close to the sun is starlight, so the problem was how to make such a measurement of stars during daylight when the sun was out. Obviously, in daylight, we cannot usually see any stars. Well, luckily for us, we live on a planet where we have a large body, the moon, which occasionally blocks out the sun, which we call a total solar eclipse. It really is a fortunate coincidence that our moon is 400 times smaller than the sun, but it is also 400 times closer. This means that when the orbits of the moon and the Earth are just right, when the sun, moon and Earth are all in a straight line, the moon's apparent diameter is exactly the same as the sun's diameter. And so the moon can block out the sun completely for a few minutes. This is when we can see a total solar eclipse in certain parts of the Earth. This won't always be the case, however. The moon is slowly moving farther away from Earth due to gravitational tidal effects in the Earth-Moon system. And in 1 million years, the moon will no longer be able to cover the entire disk of the sun. And so total solar eclipses will not occur. We are lucky to live in times when it is possible to see total solar eclipses. So how can we measure the effect of light being bent by the sun? Because stars are so far away from us, the stars appear as fixed points of light in the sky, their positions not changing relative to each other. Of course, in reality, the stars are all moving, but they are so far away that their motions only become evident to us from Earth after many thousands of years. So for all practical purposes, we can consider the positions of the stars as being fixed as we see them today. If you look at the same stars today, next year, or in 100 years' time, they will all look to be in the same position. And this gives us a really good reference background to measure things against. The idea of measuring the bending of light works like this. Let's say there are 3 stars, which we label as A, B, and C. We can measure the relative angular positions of the stars in the sky as they appear to us, with the apparent angular distance of one star from another one being measured in units of arc seconds, as we defined earlier. Hence, we can take a picture of how the stars look, and we can do this at night to get accurate measurements and without the need for a solar eclipse. Now, when we want to measure the deflection of light from star A by the sun, we have to wait for a total solar eclipse. Then, during the eclipse, if the sun is in front of star A, then we will not be able to see star A along its direct line of sight because the sun will be blocking it. But there will be a light beam from the star at some angle which just goes past the edge of the sun, and if Einstein is right, the light beam should be bent by the gravity of the sun. Once the light has been bent and we see it from Earth, it will appear to us as though it was coming from a different position in the sky. The apparent position of the star will be different to what we measured before, and it is this deflection which Einstein predicted. So in this way, we should be able to check Einstein's prediction by measuring how much the apparent position of the star changes, that is, how much the starlight appears to be deflected by the sun. This idea of using a total solar eclipse to test Einstein's theory occurred to the British astrophysicist Sir Arthur Eddington. Eddington was one of the few people who understood general relativity when it first appeared, and to his great credit, Eddington was a great champion of Einstein's theory. Even though Einstein was German and World War I was still going on when general relativity was published, Eddington recognized the greatness and importance of Einstein's work and did a lot to publicize general relativity. To test Einstein's prediction of the bending of light, Eddington organized 2 expeditions to travel to Brazil and to West Africa to observe a total solar eclipse, which was due to happen in May 1919. Eddington himself travelled to the island of Principe in West Africa, and another team went to Brazil. The Brazil expedition was hampered by poor visibility, and although Eddington himself also had to deal with bad weather and tricky equipment, he was able to measure the positions of some stars during the eclipse. After the long trip back to England, and after carefully checking his photographs, Eddington finally announced the results at a special meeting of the Royal Society in London in November 1919. The results were in agreement with what Einstein had predicted. This was the first public confirmation of general relativity and was a major triumph for Einstein. The news made headlines around the world and helped greatly in establishing Einstein's reputation, making him the most famous scientist in the world. Although Eddington proved that general relativity was correct in predicting the bending of light by gravity, it was not until 1979 that the strange effect of gravitational lensing, as it has become known, was first observed. A team at the Kitt Peak Observatory in the US found 2 identical quasars very close to each other in the sky, and tests proved that the 2 images were indeed of the same object. This was a curious observation. Quasars are the most luminous objects in the visible universe and are the result of massive black holes at the centres of galaxies devouring huge amounts of matter and emitting light millions of times more than our entire galaxy does. Seeing 2 identical objects close together led to the conclusion that what was happening was that there was just one quasar, but we were seeing double because of the effect of gravitational lensing. Something was bending the light from the quasar as it travelled to us, so that we saw two images of the same thing. The quasar that was photographed was about 8.7 billion light years away. So light had been travelling for 8.7 thousand million years before reaching us. But it turned out that direct light from the quasar was not reaching the Earth because about 3.7 billion light years away from Earth was a large galaxy which was directly in line between Earth and the quasar. What was happening was that the enormous gravity of the galaxy, the amount of curvature that the mass of the galaxy was causing in space-time, was bending light around the galaxy on two opposite sides. And so we were seeing two images of the same quasar. This observation not only further confirmed Einstein's calculations, but also allowed the mass of the galaxy to be calculated. Since we knew how much light was bent, and we knew how far away the galaxy was and the quasar was, the amount of curvature of space-time could be calculated, and hence the mass of the galaxy. And all this could be done due to the predictions of general relativity. Since 1979, thousands of other gravitationally lensed objects have been seen and studied, and this has led to one other revolutionary concept to be discovered, that of dark matter. We won't go into dark matter too much here, but suffice to say that dark matter and another thing called dark energy are two concepts that currently baffle cosmologists. We do not know what these things are, and we have no verifiable theories of what they could be, but they together make up about 95% of the entire universe. The trouble is, dark matter does not emit any light, nor interact with light of any kind, so we cannot see it or test for it. The only thing which reveals the presence of dark matter is that it causes space-time to bend, and hence it produces gravity around it. So we can infer the presence of dark matter by the gravitational effect it has on other bodies. And one of the ways we have found out about the presence of dark matter in the universe is by observing multiple images of stars, galaxies, and quasars. These gravitationally lensed images betray the presence of enormous amounts of matter which we cannot otherwise see. It is yet another example of something which Einstein predicted nearly a century earlier in his theory, which we can now use to understand the universe at large. It is amazing to think that Einstein produced the general theory of relativity in 1916, at a time when we did not even know that there were other galaxies out there in the universe, or even how large the visible universe was. But despite this lack of knowledge about the universe, or even being able to test many of the predictions of general relativity, Einstein's theory is so vast in scope, so detailed, and so complete that we are still finding solutions from Einstein's proposals today, things which Einstein himself did not even consider possible. Ideas such as the Big Bang, black holes, gravitational waves, and many more. Physicists continue to use modern astronomy and cosmology to test Einstein's predictions and the general theory of relativity. Along with quantum mechanics, relativity theory is the most rigorously tested description of the universe that we have, and Einstein's work continues to hold true today. We will continue exploring some of the ideas of general relativity in the next few videos. If you enjoy these videos, then please consider subscribing, and until next time, keep thinking physics.